Okay, thank you very much for the opportunity to be here and to present my work. That is the title, BPS Particles, Superconformal Indices, and Chiral Algebras. And today I'll present to you some work that I've done over the last 2 years in collaboration with these two gentlemen, one of them up and coming, Shuheng Xiao, and the other one, Davide Gaiotto. So let me start with some kind of general philosophy. We all know that 4D n=2 field theory is at the center of a rich and enduring interplay between physics and math. And many striking results flow from the combination of two different principles. The first physical principle is the renormalization group. So this is the philosophy that quantum field theories are organized by scale. So there's the ultraviolet, which is short distance where you define your theory. And then there's long distances, the infrared, where you want to solve your theory. And the nice part about this flow is that it's simplifying. So for instance, you could start with non-abelian gauge theory in the ultraviolet and flow to an abelian gauge theory in the infrared. Now the downside is that in general you lose information. This simplification is provably loses information. The second principle that really drives this interplay between physics and math is that there are certain supersymmetric observables that have the magic property that they're protected under this flow. So although in general you're losing information, for these very specific quantities you're not. And this leads to a variety of interesting results. But in general, if you compute a protected observable in the UV and separately in the IR, because the UV and IR are just different field theories, you obtain very different expressions for the same underlying quantity. So a celebrated example of this is the relationship between the Donaldson invariants and the Seiberg-Witten invariants. Okay, so in this talk, I'd like to present to you a new conjectural UV-IR relationship for an index I of Q. This will be a Q series that I'll define momentarily. And this Q series can be associated to any n=2 quantum field theory. And for those in the audience that know the terminology, this I of Q will be the Schur index. I'll define everything more precisely in a while, but to give you some overview of where I'm going, this quantity I of Q, its ultraviolet definition will be as a sum over local operators. And it has the rather remarkable property that if the ultraviolet theory is conformal, this I of Q will be the character of a chiral algebra. So look out for that. So that's the UV side. What about the infrared side? The infrared formulation will involve BPS particles. And here, to translate into math, I'm talking about the fully generalized and refined Donaldson-Thomas invariants. So we'll need to know about spin. And the infrared formulation of this quantity I of Q will have two ingredients. One of them is easy and the other is hard. So the easy part is that you need to know the rank R, that's this number R that will appear throughout. On the Coulomb branch, that's the number of U1s that you have in the infrared. The hard part is that you also need to know a certain generating function of BPS particles. That's this quantity trace O of Q, which I'll discuss a lot, and that will be the hero of the talk. And this trace O of Q, it will be built from this Kontsevich-Soibelman wall crossing formula. Okay, so let me just state the conjecture. It's a sharp formula. It says that the index I of Q, defined in the UV as a sum over local operators, can be recomputed in the infrared by the following formula. So here we have Q infinity. This is some eta function to 2R. And then we also have the more interesting part, this trace of the Kontsevich-Soibelman operator, this O of Q, this generating function of BPS particles. So if we apply this to conformal field theories, we're going to find that generating functions of BPS particles, that is the right-hand side, are equal to characters of chiral algebras. Okay, so this is the conjecture, and most of the talk will be about explaining and giving examples of this conjecture. And for the mathematicians in the audience, you may not understand many of the words that will follow, but I hope that you can latch on to this particular formula, which I'll unpack for you in examples, and take it home and try and understand it in your own terms. Okay, so before getting into the details, let me tell you a little bit about why I think this result is interesting. So in physics, a typical renormalization group flow starts in the UV with an asymptotically free or conformal field theory. And by the time you've gotten to the infrared, you're in a gapped or IR free theory. I should say this is for a typical RG flow. You can do some more fancy things and tune parameters and land on a CFT, but in general, you'll get to a gapped or IR free theory. And then there's this interesting fact that we think that the UV is characterized by its spectrum of local operators and their operator product algebra. This is the philosophy of the bootstrap. On the other hand, since the IR is gapped or free, its spectrum of local operators and their algebra is not that interesting, and we would typically try and characterize the infrared by its spectrum of one-particle states and their S matrix. So this naturally leads to the question of what is the relationship between these two quantities, these ultraviolet algebra of local operators and the infrared spectrum of particles. So our conjecture is interesting because it's an explicit formula relating these two concepts, which are very distinct, but provided that we focus in on the supersymmetric sector. So we don't purport to have any general idea, just that if you look at the supersymmetric local operators, a specific class of them, they are related in a certain way to BPS particles. Okay, let me continue with another slide of physics motivation. You can get an intuition about why there could be such a relationship, just a sketch, as follows. So what happens along the RG flow? So you have the UV local operators. You still have them along the flow, but the vacuum has been changed. So the ultraviolet vacuum and infrared vacuum are different. Now, given a local operator, you can consider a state where you act with that local operator, a UV concept, on the infrared vacuum. So call that state psi. And you can just see from this equation that since the vacuum is supersymmetric for the flow I'm considering, if the operator phi is supersymmetric, so is the above state psi. Now, although this is a supersymmetric state, it's not a standard one-particle state. That you can't make a one-particle state by acting with a local operator, or at least just a one-particle state. Instead, you should think of this state psi as a multi-particle state, which is something like a jet of BPS particles. So it's an outgoing S wave of various different particle numbers. And this idea can be made precise for 2D quantum field theories, and I think it's an interesting direction to explore in higher dimensions, and especially to zoom in on this supersymmetric sector where we have a concrete relationship in mind. Okay, that was some physics motivation. What about some more mathematical reasons why this can be interesting? So BPS particles are, of course, widely studied, and they have many different presentations. Usually they come as cohomology of moduli in an appropriate sense, and what moduli spaces you're studying depends on how your problem is presented. So here are a few. You can have monopoles, quiver representations, coherent sheaves, special Lagrangians, spectral networks. No doubt there are some that I left off, and more to be invented. These constructions all depend on a central charge, mathematically a stability condition, and the central charge can be varied in a finite dimensional complex moduli space, and BPS, the particle spectrum is locally constant, but jumps across walls of real codimension 1. And this is really a feature, not a bug. This is the expected physics and mathematics of these invariants. And so it's natural to ask, in general, what wall crossing invariants exist and what are their properties? So this problem was essentially solved by Kontsevich and Soibelman, And they constructed an invariant O of Q, which is some kind of operator valued in a quantum torus algebra. And I'll review the definition of O of Q momentarily. And one of the reasons why our conjecture is interesting is that it links this universe of BPS states and wall crossing to vertex operator algebras, which is a completely different universe. Okay, so we're done with the motivation. We're done with the slogans. Let's get into some details. So first, let me define the index for you. So every n equals 2 theory has a operator spectrum that can be graded by 3 distinct SU2s. SU2R, SU2J1, and SU2J2. The R is the R symmetry. J1 and J2 are the 2 spins in the Lorentz group. And so if someone hands you a quantum field theory defined by its spectrum of local operators, you form the following sum. And this is how you define I of Q. It's a function just of this one variable, and it's a series in square root of Q, because these R's and J's take half integral values. What are some of its general properties? So as advertised, I of Q is an index. That means that it receives contributions only from 1/4 BPS local operators. That's just because I put this -1 to the f here, so operators that are in long multiplets will cancel in this sum. If you're in the special case, which I'll mainly focus on today, of superconformal field theories, then this index coincides with a limit of the superconformal index, which is called the Schur limit, and it's been widely studied in physics. Now, one of the nice things about having a quantity that's an index is that if someone hands you a Lagrangian field theory, you can immediately compute I of Q. What's the logic? The logic is simple. Since it's an index, it doesn't depend on marginal couplings. So you can go to the weak coupling point, the free point, where you know the operator spectrum, and then you can immediately write a formula. The final property of I that I want to mention here, which is crucial for my story, is that its definition relies only on these 3 SU2 symmetries. And these symmetries are preserved on the Coulomb branch. And that's a crucial feature if you want to reproduce this index in the infrared. So we're going to rely on that fact heavily. Okay, that's the definition. Now there's a remarkable result by these authors that says that I of Q is the vacuum character of a 2D chiral algebra. So just to give you some details about that algebra, so first of all, we know its central charge. The 2D central charge is -12 C4D, where C4D is the number defined by this 2D, this 2-point function of stress tensors. And it follows that in general, C2D is less than 0. So for every 4D n equals 2 theory, n equals 2 conformal field theory, this index is the vacuum character of a non-unitary 2D chiral algebra. Yeah, I should say that it's important for this result to be true that we're talking about a conformal field theory. So for those of you not steeped in this literature, let me give you a few examples of this dictionary. So the first 2 are free fields examples. So if you have a free vector multiplet, the associated chiral algebra is the BC ghost system. And the character is Q infinity squared. For the other free fields, for n equals 2 free fields, hypermultiplets, you get anti-commuting bosons. And the character I've written here, and I've introduced a new variable z, which is the flavor fugacity. You can weight the local operators by their U1 charges. And this function will appear over and over again in the rest of my talk. And it's a famous function. It's the so-called quantum dilogarithm. And for those of you who know a little bit about wall crossing, you can already see that some ingredients of wall crossing formalism are creeping in here, this quantum dilogarithm in particular. So those were 2 free field examples. Let me now show you a more interesting interacting example. You can consider SU2 QCD, with 4 fundamental flavors. That's a conformal field theory. And the associated chiral algebra is this affine Kac-Moody algebra, SO8 at level -2. And there is a remarkable expression for the associated character in terms of Eisenstein series. Okay, that was the index. That's the UV side. We know now its properties. Let's now talk about the BPS particle side of the story. So what are the ingredients there? Well, we have the Coulomb branch, and as we've discussed, we have a U1 to the R gauge theory. So R is the rank. And you should think of the Coulomb branch as some kind of generalized version of electromagnetism. There are massive charged particles, but they carry both electric and magnetic charges. So these charges, gamma, are valued in a lattice, and this lattice is equipped with an antisymmetric Dirac pairing, integer valued. The BPS particles are encoded in a collection of positive integers, omega n of gamma, and you can just think of this quantity as the number of BPS particles of spin n and charge gamma. Now, of course, these invariants, so again, let me emphasize that because I have the n here, I'm talking about refined invariants. These invariants jump as moduli are varied, and invariants, that is, wall-crossing invariant combinations of these indices, were constructed by Kontsevich and Soibelman, and we're going to make heavy use of their formalism, which I'll now review. So their formalism makes use of non-commutative variables, x gamma, and they obey this algebra. X gamma prime is x gamma prime x gamma, but there's a correction factor q, and this correction, the power here is this Dirac pairing that we had before. So this formula will come back again, so try and remember it. Okay, so what's the lightning statement of the wall-crossing formula? So for every charge, you introduce a factor, k gamma. So what does this factor look like? Well, we've got the quantum dilogarithm function, this EQ, but now instead of evaluating it at an ordinary variable z, we're plugging into its series expansion this non-commutative variable x gamma. And then we have a power here that depends on the BPS particle degeneracies. So for each charge gamma, we form this quantity k gamma. And then we make the phase-ordered product. And we order it by the central charge phase. So since these variables are non-commutative, we need an ordering, and that's guaranteed by the, or given by the central charge phase. And the statement of the wall-crossing formula is that this quantum torus valued object, O of Q, is wall-crossing invariant. Okay. That's a nice invariant, but it's a bit complicated because it's valued in a quantum torus. It would be nice to latch on to some simpler invariants to explore. And some simpler invariants were first constructed by Chakotay, Knightsky, and Vafa. So you can take a trace of this object O of Q. What's a trace? So trace is defined on the quantum torus algebra as follows. It's very easy. It's 1 if the charge happens to be 0, and 0 otherwise. So for most elements, it's just 0, and then you extend by linearity. And now the trace of O of Q is kind of an interesting object because in this product, we'll sometimes have a particle gamma, and then far away in the product, because of the phase ordering, we'll have an antiparticle with charge minus gamma. And we have to bring them together to find the coefficient of 1 to evaluate this trace. And so this is a kind of familiar normal ordering calculation in physics, and it leads to interesting invariants that we're going to talk about. This O is defined as a product all around the circle. Later, half monodromies will appear. The fact that, so the choice of starting phase drops out in the trace. Okay, so this was a review of the wall-crossing formalism and the invariant that we'll focus on. Okay, so let me now show you an example of the conjecture in action. So the simplest non-trivial example is the so-called Argyres-Douglas CFT. This is a strongly coupled interacting theory. Geometrically, it comes from type 2b on this singular Calabi-Yau hypersurface. UV is y squared plus x cubed. And we know the central charge of this system, that's C4d, so we can plug in to the formula and learn what the central charge of the associated 2D chiral algebra is. And you find by some numerology that this is the same as the central charge of the Virasoro minimal model, the 2,5 Virasoro minimal model. So let's run with it. So on the Coulomb branch, there's a single U1, and the BPS spectrum of this theory has been well studied. It can be computed in a large variety of different ways. So you could take this geometric definition and resolve the hypersurface and compute the compact special Lagrangians. Relatedly, you can look at spectral networks or WKB curves. In this case, they would be on a pentagon. And you can also explore the representation theory of this simple quiver. And depending on the stability condition, the central charge, there are either 2 or 3 BPS particles, and they're all hypermultiplets. None of them carry spin. Okay, so now we can just try and investigate the answer. So let's test this conjecture. So the 2,5 Virasoro minimal model has a vacuum character that's a well-known Rogers-Ramanujan function, has this following definition. Maybe I should comment that I've put this normalization factor here because my index should start from 1. So I chose this power to make it start from 1. On the other hand, if we grind through this trace of the KS operator, we obtain an expression like this. So it's pretty easy to do. You get a double sum. And okay, these obviously look nothing alike. So we need something of a miracle. So you expand it out, and you get your miracle. And by now, there exists an abstract proof that these two expressions are in fact equal to all orders in Q, not just to some order that I was able to check in Mathematica. No, in general, they're not positive integers. This is a simple feature of easy examples, but it's not in general true. More questions? Okay, so there are many, many other examples that have been investigated where both sides can just be computed in detail. So continuing in this theme of Argyres-Douglas theories, you can look at this kind of hypersurface where you increase the powers of x and y. That's this Argyres-Douglas theory. And if n and m are co-prime, you find a match to the n plus m Wn minimal model. The vacuum character, that is. And you can look at other hypersurface singularities defining other Argyres-Douglas theories, and they give rise to other well-known chiral algebras. So for instance, the Brzezinski-Polyakov algebras and SU2 affine-Kac-Moody. Another direction that's also interesting to explore is our Lagrangian examples. For instance, I advertised this Eisenstein series formula for SU2 with 4 flavors. And so that example is nice because it's a Lagrangian field theory. You can just sit down and compute with your hands the index I of Q. On the other hand, the BPS spectrum in that example is known, and you can compute and check that the conjecture is working. Okay, so one of the things I'd like to emphasize, especially to mathematicians, is that this conjecture is completely general. So although I've only checked it in a few examples, it's supposed to be independent of where your example comes from. It's supposed to apply to any n equals 2 quantum field theory. So whenever you have any geometric setup that gives you an n equals 2 superconformal field theory, you will find that this invariant of BPS particles that I've produced is a vacuum character of a chiral algebra. It might be hard to figure out which chiral algebra, but it's basically guaranteed, provided the conjecture is true. Okay. Yeah. Yes. So the more tricky point that you should ask me is that is it obvious that O is well defined? So Kontsevich and Soibelman discussed half-space monodromy operators, and I discuss the full circle monodromy operator. So really, the correct technical definition of O involves, and the trace involves taking an expansion of products of S's. So let me say this. It's if you believe that S is well defined, the half monodromy operator, then you should believe that trace O is well defined. Okay. All right, so I've given some computational evidence. We have a statement, but I've given you nothing even resembling any argument about why this should be true and how you would ever be led to a statement like this. So let me turn to that now. So how can we understand this formula? How did we even cook it up? So let me present an intuitive physical argument towards that direction. And I should stress that this is intuitive. It's not a rigorous argument, but it will motivate the two sides of the equation. So as I said at the beginning, you should think of this formula as computing the same quantity I of q, the index, from the infrared point of view. So how are we going to do that? Well, we're going to proceed in the most naive way possible. We're going to use the effective Coulomb branch description, this u1 to the r QED, and try and compute the index by treating the BPS particles as independent fields. Now, this looks like a silly thing. The BPS particles are both electrically and magnetically charged, so you can't write a Lagrangian for them that has this feature where they would appear as independent fields. Nevertheless, you can still use this logic to obtain a formula for the index. So I'm not trying to do too much. I don't need this Lagrangian. I'm just trying to compute an index. This is kind of similar to Gopa-Kumar-Vafa type inspired logic. Okay, so if we're going to do that, if we're going to look at the index for QED, really all we need to know are indices for free fields and how to build them up. So let's start with the free fields. I highlighted them before, but I'll bring them back. So here is the U1 vector multiplet. We get this power of the eta function. And here, for the half hypermultiplet, we get the quantum dilogarithm. That's what's driving the show. And so if you wanted to compute the index for U1 QED, it's very straightforward to do. So here you have the contribution from the vector multiplets. Here you have the contribution from words in the matter fields. There's one of charge 1 and one of charge -1. That's the two exponents here on Z. But Z is now being gauged. It's a gauge theory. So I don't want to keep all words. Rather, I want to project onto gauge invariants. So I do a little contour integral. And this simple formula is the index for QED. And our goal is just to write a very similar formula taking into account magnetic charges. Okay, so here's the key moment. Suppose we have a hypermultiplet field of charge gamma. You could think of it as electric for any given charge, but we're going to have to confront the issue that there are mutually non-local charges, both electric and magnetic, in the spectrum. So what we need to do is come up with a rule to assign quantum numbers to composite operators. After all, most of the operators in the index are composites built out of the elementary fields, and we need some rule for their quantum numbers. So if we have a product, H gamma prime, we're going to declare that this quantity should have electromagnetic charge, gamma plus gamma prime. So the electromagnetic charge is additive. But we want to put in an extra bit of spin, a half gamma inner product gamma prime. And what is this doing physically? This is taking into account the fact that these particles source a long-range electromagnetic field that carries angular momentum. And after all, the Dirac pairing is the thing that computes the angular momentum in the electromagnetic field. So that's what this assignment is doing. Now, if you want to have these charge assignments in calculations, in index calculations, it's quite simple and useful to introduce non-commutative variables. So Q counts angular momentum in the index. And so what we want is that x gamma prime is Q to the 1/2 gamma prime, x gamma plus gamma prime. And this is mimicking these charge assignments. Okay, so we're ready to get to the formula. So we now assemble the pieces. So we'll be led to this formula. So here, where do the ingredients come from? You should think of this as a direct analog of the QED formula that I wrote before. So q infinity to the 2r, that's the part from the vector multiplets, that's easy. Then we have these EQ factors accounting for the hypermultiplets, but since I want this funny assignment of charges, I evaluate them on these non-commutative variables. And finally, I need to project onto gauge singlets, just like I had to do an integral for QED. And that's accomplished by this trace operation, which just selects the coefficient that has vanishing charge. Okay, so I should also mention here that my charge rule, I solved one problem, but I introduced another, which is that since I'm using non-commutative variables, the order is crucial. And here, I'll just take it as an ansatz for the purpose of this talk to match onto the KS formalism that you should phase order it according to the central charge. There are many comments to be made about how to see that from the infrared, but I don't want to go into that right now, maybe afterwards. Okay, so this is the desired infrared formula. In case it's not clear, this quantity here is the KS operator in the special case where everything is just a hypermultiplet. And although I did it for just hypermultiplets, you can easily generalize it to the case where the BPS particles carry spin. So this is the physical, intuitive physics picture of how you could be led to this formula. Questions? No? Okay, so now I'd like to discuss some generalizations. Sorry? Yeah, to write the index of a massive spinning particle. Yeah, I think, well, okay. So let me, what I've just discussed to you is basically the first of 4 papers, and there are 3 others, and what are they about? They're about generalizing to defects in various different combinations of that. So I'll now discuss that, and we'll work up in dimensions, starting with lines. So n equals 2 theories admit a class of half BPS line defects, and we can build an index IL of Q that counts quasi-local operators that can end the defect. So not operators on the defect, but these are like ray operators. This is the closest thing you can make to counting charged fields in a gauge invariant way. So we can extend this UVIR conjecture to lines, and the extension looks as follows. So here we have the same KS operator, same eta function power, but now we've got an insertion, FL of x gamma. So you think of this as the contribution from the line. And what is this quantity? This is the generating function of framed BPS states. So roughly speaking, you can think of these framed BPS states as ordinary BPS particles bound to a heavy line, a heavy probe. And these are related geometrically to framed quiver representations and framed DT invariants. Okay, why is this conjecture true? Well, the logic of the conjecture is identical to the heuristic physics picture of the original conjecture. So under RG flow, the line defect L decomposes into a sum of infrared lines. And these are dions, and you can think of these as the x gamma. And the linear combination into which L decomposes is controlled by the frame generating function, FL of x gamma. So if you want to compute the index in the infrared in the most naive way possible, you would just compute the infrared abelian index in the presence of a sum of dionic line defects, Wilson and 't Hooft lines, and then you just sum them back up according to this generating function. And that's exactly what is happening when you insert FL into the trace. In the index? S1. In the S3 times S1 geometry? Yeah, this is S3 times S1, where you have a line at a point on S3 wrapping the S1. So conformally equivalent to a ray in space-time. Okay, so we've extended the conjecture, and what kind of interesting results do you learn? Well, you learn some magical facts about the line defect OPE. So line defects admit a topological operator product expansion, these BPS line defects. And these OPE coefficients, these Ci, J, K of Q, can be determined by multiplying the associated frame BPS generating functions. And here's an experimental fact that we found that we don't have an explanation for. So the OPE algebra of line defects reproduces the Verlinde algebra of the associated chiral algebra at the level of indices. So what does that mean in a concrete formula? If you take the index of, in the presence of a product of two line defects, and you try and re-express it as a sum of indices in the presence of a single line defect, then you find that the coefficients that you need are the Verlinde coefficients of the chiral algebra. Okay, let's move up to surfaces. So we can also extend to BPS surface defects. And in this case, our results will intertwine with the Chakotay-Vafa formula for the elliptic genus of a 2-2 theory in terms of BPS solitons after relevant deformations. So to do this, we're going to need the so-called 2D40 BPS states. And they're defined as follows. So your 2D defect will have some number k of massive vacua, and there are solitons that can go from vacuum I to vacuum J, distinct vacua, and also particles that can go from vacuum I to vacuum I. And these 2D BPS objects can carry bulk electromagnetic charges. And so that's why they're called 2D40 BPS states, because they interplay between both 2 and 4 dimensions. And there's a natural conjecture if you want to compute the index of local operators bound to the surface defect. You just form an analogous statement where here O2D4D is a k by k matrix of wall crossing operators. So its various different components encode the various 2D4D BPS states going from vacuum I to vacuum J. So this is a very similar conjecture. Surface defects are interesting in the relationship with chiral algebras because they have a nice interplay. So if you have a conformal surface defect, the local operators on the surface form a module for the chiral algebra, and the index IS of Q is again a character. But in this case, it's not usually the vacuum character. So in the case where we were just considering the ordinary index I of Q, it was a theorem that we should get the vacuum character. But now, which character we get depends on which surface defect we put in. And natural operations like spectral flow and Drinfeld-Sokolov reduction at the level of chiral algebras have interpretations at the level of surface defects. And so there's a nice dictionary there relating to monodromy defects and vortex surface defects. So let me give you a simple example, again, in this A2 Argyres-Douglas theory, which was related to the 2-5 minimal model. So we saw the index without a defect, but now let's look at the surface defect. So there's, in the class S world, a thing called the canonical surface defect. Don't worry if you don't know what it is, it's just some surface defect. And you can compute its BPS states and grind through this calculation, and you get this formula. It looks almost identical to what we had before, except for here I have just this factor in parentheses, this 2 minus q to the L1, whereas for no surface defect I didn't have that factor. And you can evaluate it, and miraculously this is equal to the character of the non-trivial primary of the Virasoro 2-5 minimal model. Okay, so let's keep going. We can get an interesting relationship between surfaces and lines. So here's a picture of a 3-sphere. That's this big round circle. The dot is the center. And the blue thing is a surface defect wrapping some great circle in the 3-sphere. And the index is in fact invariant under an interesting sequence of maneuvers. So you can cut a surface defect here by putting in a complete set of supersymmetric boundary conditions. And then you can unwrap the defect around the sphere and then close it up and collide them. And when they collide, you're back to this initial geometry that I was talking about being related to line defect indices. So what this maneuver shows you is an interesting relationship between line defect indices and surface defect indices. It says that a surface defect index is equal to a sum of line defect indices. And if you're in the special case where you have a conformal field theory, and a conformal surface defect, of course, we've just discussed that this quantity here is a character. So this shows that also certain sums of line defect indices are guaranteed to be characters of chiral algebras as well. And if you try and discuss this in the UVIR formalism that I've been advertising today, you'll necessarily need to introduce framed 2D40 BPS states into your calculation to account for these boundary conditions B here. Okay, so we're now working up. Now we're at boundaries. So there's a general interesting point that by exploring defects, we are interpreting more and more components of this quantum torus valued wall crossing operator O as indices. So we started with just seeing trace of O as some index. Then we had trace of O with some insertion as an index, and so on. And it's natural to ask if there's some index-like way to interpret all the components of this wall crossing operator O. And this can be achieved through boundary conditions. So let me define a very interesting boundary condition B. It's a boundary condition defined for the UV quantum field theory, and it has the property that it flows to a Dirichlet boundary condition for the U1 gauge fields. So this is sometimes called an RG boundary condition in the literature. So this is some UV boundary condition, and you could try and compute the index in the presence of this boundary condition B. Now, on the boundary, because I've put Dirichlet boundary conditions for these U1s, I get flavor electric and magnetic charges for each of these U1s. And I can form a generating function of all the indices that I can compute in different flavor sectors of various of these different U1s. And if you sum it up, what you find is that index, that generating function of indices, is literally equal on the nose to the KS operator, S. So this S is the product over half of the central charge space. So this is conceptually rather interesting. It gives a completely new physical interpretation of the wall crossing operator, and it does so in a way that's completely intrinsic to the UV QFT. So you don't have to go on to any moduli. You can just insert this boundary condition and compute the index, and that is what this KS operator is. This is, if I want to write this as a path integral, it would be a half S3 times S1. And the boundary condition B lives at the S2 times S1 boundary. And because there's an S2, that's why I get to turn on these flavor electric and magnetic charges. It's, well, why is this relation true? I just didn't hear your original question. Oh, I'm summing it up. So I fix an electric and magnetic charge sector, and then I get an index, which is just some function of Q. And then I weight that index by x gamma, where gamma has the electric and magnetic charges that I'm interested in, and then I sum over gamma. And that's what this generating function is. Right, so I'm telling you that the coefficients of each term in x gamma, each coefficient has an index meaning in this geometry. That's the nice part about this. In many places to cook up this statement. So this boundary condition intertwines UV objects to IR objects. So if you bring line defects through it, nice things happen to them. It's an interface. You can think of it as an interface between the ultraviolet theory and the infrared theory. So I'm using that property. Okay, so that's the end. I guess I'll end a bit early. So many open questions remain. So of course, the most glaring is to prove all this UV-IR nonsense that I've been talking about. So to that end, it's very useful to interpret this index as a partition function. Of course, at the superconformal point, that's guaranteed, but I'm quite interested in the index not at the superconformal point. And so it's useful to interpret it as a S3 times S1 quantity. And there's some promising upcoming work in that direction. Another question that I think is fascinating is that if you have a superconformal field theory that is related to a Calabi-Yau geometry, then there should be a widget that spits out a chiral algebra from that geometry. And we don't know what that is. It would be really nice to have a concrete construction. And finally, I've given you evidence that you can construct characters from BPS particles, but I've given you no evidence that you can construct a full chiral algebra, that is the operator product expansion coefficients. It would be very nice to fill that gap. So thanks for listening.